Bismillahirrahmanirrahim. Assalamu alaikum students. How are you? I hope you will be fine and you will be enjoying the electrostatics because we are dealing with electrostatics and different phenomena in electrodynamics and electrostatics. And today we are going to discuss the force on a point charge embedded in a dielectric. Means if we have a dielectric medium, if we have a dielectric material and a charge is embedded inside the dielectric material, then what will be the force on that charge due to that dielectric medium? Means we have a volume and inside a volume. This is very finite volume. This is not on the macroscopic levels, but it's very smaller volume, and we consider a charge embedded inside the volume. We will determine the force on a small spherical charge conducted embedded in a linear isotropic dielectric. Means very small charge, as very small spherical charge conductor is placed inside the dielectric medium, the medium that is linear and isotropic. In the limit in which the conductor is negligibly small from the macroscopic viewpoint, means the material that you have embedded inside the dielectric is very small, negligibly small. This calculation gives the force on a point charge that we are going to deal right now. The calculations, what will they provide? They will provide us the force on a point charge. And the electric field and surface charge density at a representative point of conductor. What is that point? In the volume, you have placed a conductor and you are dealing with only that point at which the conductor is placed, is embedded inside the dielectric. This is what? At a representative point of conductor is obtained by the boundary value procedure, and the force F then we obtain from the integral over the surface. So we will determine electric field, surface charge density and force on that embedded conductor using the boundary value problems and this formula for the force. And this force F is equal to surface integral E prime sigma dA. This is our equation number 1. Here E prime stands for the electric field at the surface element dA. Means on the dielectric you have considered a smaller surface area dA. So this E prime is electric field at that point, that surface area dA minus that part of the field produced by the element itself. And a portion of the electric field will be produced due to the material embedded inside the dielectric, the conductor that you have placed inside the dielectric. Some electric field will be produced due to that material. So electric field E prime will be electric field at that surface element dA minus the electric field produced by itself, the conductor. Then the net field E prime will be equal to E minus ES. ES is the electric field at that surface that you are considering. It may appear that the self-field of the charged surface element sigma dA. Sigma surface charge density. dA is the surface. When you multiply the surface charge density with the surface, you get surface charge. Q is equal to sigma into dA. That's why we are talking about the charged surface element sigma dA is negligible because the element is of infinitesimal size. We have already defined that element is very smaller. At a point directly on its surface, the element appears as a section of the plane, just like this. This is the surface that you are considering for the calculations in the dielectric medium, and ES and ES prime are the self fields produced due to the conductor placed inside the dielectric. The field ES, this one, is perpendicular to the element. If this is element, then electric field will be perpendicular to that element. The total field inside the conductor is 0. Not inside the dielectric, but inside the conductor, the total field is 0. Mean E prime minus ES is equal to 0. This equation provides a relation between E prime and ES on the surface, and hence between E prime and macroscopic electric field E at the surface. How? This E prime will be equal to E minus ES, because we have written over here E prime is equal to E minus ES. We will use the same equation over here, and it will be equal to half E. And E, by using Gauss's law, has the value sigma over 2 epsilon, n unit vector, normal vector. Now, you can use this E prime in equation number 1 here to calculate the force. This is the electric field and this is the force. To get the force, F, just plug this value of E prime into this equation. You will get the force on the conductor. F is equal to half sigma E sigma D. So it's just half of the integral E sigma dA. Sigma dA is the charge Q, is being multiplied with the electric field E. QE. F is equal to EQ. We know that the formula of force is equal to Q multiplied by electric field E, and the same is over here. But half with half. This is the boundary condition that we have studied earlier in this chapter. Has been applied to calculate the force on the conductor placed in the dielectric, not on the whole dielectric. So this was our today's topic to discuss. If you have any question, you can ask me. Later on, if you have any question, you can ask me via my WhatsApp number and in the description as well. Thank you very much.